Okay, thank you for introduction. I'm Miwako Tsuji from RIKEN Center of Computational Science. So I'd like to talk about kind of update of our Quantum-HPC hybrid platform, which started in last April. So this is an agenda. So actually my talk is a bit shorter than other two presentations. So that I would like to talk about the overview and the current status of our project. And after that I will talk a bit detail about our design and implementation of Quantum-HPC software to connect to the two systems. So we have conducting two projects related to Quantum-HPC. So one is called TORIP. So this is a RIKEN internal project to connect several research institutes or research facilities to accelerate the research. So, and especially we are focused on the RIKEN's R-CCS Center for Quantum Computing Centers, superconductive quantum computer, and supercomputer Fugaku in R-CCS. The other one is, we call it a JHPC Quantum. So this is a project conducted under the NEDO, so which is an agency of the Ministry of Economy, Trade and Industry. So, and in this case, we connect supercomputer Fugaku and two commercial quantum computers. And the characteristic of JHPC Quantum is that we are oriented to provide early commercialization of quantum computers and make use of a quantum computer for social applications. Of course, with supercomputer. So in total, this diagram shows a whole system in our platform. So Kobe. So we are now in Kobe, and we have supercomputer Fugaku, and we are now installing the superconductive quantum computer from IBM. And we will install the GPU cluster in next autumn. And in Miwako, the main campus of RIKEN, we have a superconductive quantum computer developed by RIKEN, and we will have quantum trapped ion type quantum computers. And these are connected through the internet. And as well as these supercomputer and quantam computers, we will connect supercomputers in universities, University of Osaka University and University of Tokyo. So, and this is a status of our quantum systems procured by NEDO project. So, we will have two quantum computers. One is IBM Heron. So this is a superconductive quantum computer of 133 qubit. So, and the current status is that we are ready. The room to install this quantum computer is now ready. And in case of Quantum, so this is, we will have a system model H1. And this is a trapped ion type quantum computer with 20 qubit. And as already shown by Satoshi Matsuoka in this morning presentation, so we are already bring everything from United States to Miwako and constructed it, and now we are they are calibrating and tuning the system, and we will start operation with this quantum computer in February. So it's very soon. And in case of IBM, the room is ready. So this is the room for the IBM quantum computers. This is just under the supercomputer Fugaku. So this is not the Apple Store, but the room for the quantum computer, and we will have something like this in the next May or April. So we briefly review our Quantum-HPC programming model. So this is already talked last year by Mitsuhisa Sato. So we decided to adopt the two-level programming model. And first level is workflow. And second level is task-based parallel programming. So in workflow, basically, task is a kind of job submitted to the job schedule of supercomputer or quantum computers. And so task will be workflow, which involves several different kinds of jobs, and we provide several workflow engines to manage the job submission. So, and we expect three kinds of jobs in our workflow. So one is a simple HPC job running on kernel only on HPC. Another one is a simple QC job. It just offloads a quantum circuit to quantum computer. The third one is a HPC quantum hybrid job, which include both HPC and quantum kernels. So why we do need this kind of the programming model? So the reason of the first layer is that a basic idea is that we try to avoid waiting time in both quantum computer and supercomputers, because both of them are very important and shared computational resources. So that if we if a workflow manager contact with job scheduler, then a job scheduler dedicated to each system may arrange this kind of job to maximize the throughput of their systems. So originally, we plan to have a co-scheduler which which reserves the computational resources in both HPC and quantum computer simultaneously, something like this. But if workflow is something like this, HPC, quantum, HPC, and so on, then we could not avoid the idling time, at least one of the computational resources. So on the other hand, if the workflow manager work with a job scheduler dedicated to each of the HPC and quantum computer, then we can make both of the computational resources always busy. So this is the idea of the first layers. But we need the second layer of the more tightly coupled quantum and HPC applications, or maybe the iterative algorithm of the quantum HPC, which flows the kernels, many times in a short time frame. So in such case, it may be difficult to wait the job scheduler invoke circuit executions or HPC executions. However, in this case, we still have a problem of the waiting time in HPC. So for example, if application is something like this, but if a quantum computer is busy, then HPC have to wait the quantum computer available for him. But as you know that, as a worst case, Fugaku consumes more than 20 megawatt per hour, and to make the 20 megawatt just waiting is a very stupid idea. So that we allow the request from quantum computer cut in all the waiting queue of the independent quantum circuit executions. So, and to manage such kind of the prioritized scheduling, before the quantum backend server, we decided to place our own quantum request schedulers. So all the request is basically managed by workflow manager, and this workflow manager submit job. If it just includes a single quantum job, then it is submitted to the queue. And this queue is submitted to scheduler, but with low priority. And if a job includes the HPC and quantum, this workflow manager submitted to the supercomputer, and the supercomputer offload quantum part of HPC and quantum hybrid job to scheduler with very high priority. So actually, this is always pole position of waiting queue, and executed immediately right after the quantum computer is available. So then we can avoid the waiting time here by controlling the priorities. And this diagram shows the system configurations, whole system configuration. So it's a bit busy. So we have several servers. One is workflow server and one is front end. So it may make us available to submit some special queues dedicated to quantum HPC job or general HPC job of the Fugaku. Actually, we already reserved 29 nodes of Fugaku as a special partition, which basically our HPC quantum user can exclusively use. And each of the queue can submit the job to quantum computer, IBM quantum computer, as well as a simulator will be available next autumn. And the job which involve only the circuit execution is once submitted to a queue, the same as the different HPC quantum job, and then go to the this quantum RPC request servers. And additionally, in addition to Fugaku, of course, the supercomputers in university can access this quantum computer and submit the job to the quantum computers. So most important part of this idea is a request schedulers. So this diagram shows the quantum RPC request schedulers. So within scheduler, we have three threads. One is dedicated to the RPC communication between client, and one is a scheduler, and one is invokers, which offload jobs to quantum computer through several APIs. So actually, we will launch different scheduler for different quantum computer. So it means that there are 4 independent invokers, but only one will be activated for each in each QC request schedulers. So first, user submit a job through RQC request, and then the scheduler may register job in our database. At the same time, the job is sent to the scheduler, and if the job is high priority, then it is immediately sent to the invokers. If it is a low priority job, then it is in the queue and waiting their turn. And after that, our invokers may communicate with a quantum backend server and post job and get the result. Result is registered this registers to our database, and the RPC get a result from the database and send back the result to client. So this is our scheduler. And between scheduler and quantum backend server, we will provide 2 different options to 2 different quantum hardwares. So one is cloud. So cloud service is an existing cloud-based service. So the server will be somewhere in the world, so we do not know. Maybe it's Amazon East or something. And the other one is a direct access service. So it may be faster connection through direct local connection or a virtual local connection. So actually, we will have IBM's quantum computer here under the Fugaku computer room. And in case of the quantum which is placed at the Miwako, so we will connect it to a virtual local area network. And QC request scheduler may have in charge of the communication between cloud or cloud-based or direct access service. So we developed several invokers implement with REST C++-based SDK by Microsoft and gRPC SDK respectively, and support a very basic function to submit a job, or check the status, cancel job, and delete a job. So from the viewpoint of the RQC request scheduler as a client of quantum computers, the job is basically blocking. Because if after we send the request to the quantum backend server, there's no room for job scheduling from our side. So to avoid such things, the job submission from quantum scheduler to quantum computer is a blocking one. And from the about the authorization, so its quantum system authorizes the quantum request scheduler. So it means that a quantum computer server does not authorize a user. So user authorization will be done in the quantum request scheduler. So this is from user side. So between our library and quantum request scheduler, there's authorization as well as several circuit execution and communications. So users are authorized by the quantum request schedulers. And all the required functions are included in our library. We call it supercomputer quantum computer computation library, SQC library. And basically, users do not have to care about the authorization or job submission to scheduler and so on. So this is an example of the API supported by our SQC libraries. So the first part shows the quantum circuit construction. So basically, if users use this one, we expect that the user may write their program by C or C++, or in future it's hotline supported. It means that this is designed for quantum HPC. So that's not Python, but the HPC language is preferred in our programming environment. Of course, the Qiskit or ticket is also supported in Fugaku. And after the circuit construction, it will be sent to the quantum computer backend server, and users do not have to care about the communication or different communication interface of cloud or direct API and so on. So at the end, I'd like to introduce our schedule. So something important is that so we start the trial operation from next April, and we may call the test users for this our test bed. So if you are interested in, please check our symposium. So another important announcement is that our JHPC quantum project will have a symposium in next month, February 20 in Tokyo. And so the registration is open, and you can access our website and have more information about our project. At the end, I would like to thank the Supercomputer Fugaku User Program as the NEDO project.